So section 3.5 is going to shift gears a little from what we have done previously in chapter 3. So chapter 3 so far has been primarily focused on what we call identities. So identities are equations that are true for every variable. The left-hand side looks exactly like the right-hand side with some manipulation so that you can see really they're just the same thing. Right? That's what an identity is. An identity is where the left-hand side and the right-hand side are the same, but they look different. And we do this with numbers all the time, right? So 6/2 is an identity for 3. It's exactly the same thing, just looks different, right? And we've talked about that at different points. Trig actually has that property as we go around the unit circle, right? Over and over and over again, we get the same sign value every single time it hits these certain spots, right? This identity that the sign of, let's do the sign of 0 is exactly the same as the sign of pi. And in fact, it's the same as the sign of any whole pi value. Every single one of them are exactly the same. They just look different. So this section, what we're actually going to be looking at are equations where they're not like that. So these are more like the traditional equations that you remember from algebra, okay, where you're looking for the value that actually makes it work. It doesn't work all the time. Maybe it only works for one time. In the case of trig, they're going to work often for multiple answers, but not for all possible answers. Right, the left-hand side and the right-hand side are not going to be exactly the same in all possible scenarios. We're actually going to be finding what angle makes this work. That's the goal for section 3.5, okay? So let's take a look at our leading idea. Solving trigonometric equations often means working patiently through steps, sometimes facing multiple possible answers, which will happen, or complicated expressions, which is going to happen too. We trust the process and mathematical tools to guide us to the correct solution. And you guys have lots of mathematical tools to do that. And I'll keep pushing back into that, both from knowledge before this class and algebra classes you've had, and from things we've done in this class. So we're going to see both of those. Faith in God is much like this. Sometimes life feels complex and uncertain, and we don't immediately see the answer or the path ahead. But by trusting God and being patient, we find clarity and purpose over time. Just as mathematics eventually reveals the solution, faith leads us to understanding, even in difficult times. Let's pray. Dear Heavenly Father, I thank you so much for these students. I do thank you for the break that we had, and I thank you for their diligence and their perseverance in just getting up this morning. It was a struggle in my house, and I know for some of them it was a struggle as well, and I just thank you for their dedication to their studies and for the calling that you've placed on them to be here. I pray that the material that we work through today would have those connection points, that I would be able to effectively communicate places that draw upon previous knowledge and levels of understanding and make connections that maybe not otherwise have seemed obvious. I pray that you'd be with our class session today and that everything we do would bring honor and glory to you, Jesus. In Jesus' name I pray. Amen. So some basic strategies that we're going to use for solving trigonometric equations are the following. So the first one is to decide often if the equation is linear or quadratic. Okay, so linear means it doesn't have any powers, right? Powers of 1. So when you're thinking linear equations in algebra, it would look like this, y equals x plus 2. That's a linear equation. It's a line. And so we see things like that. If we were looking at solving equations, it might look something like, x plus, well, let's do 2x. We'll make it more interesting. 2x plus 3 equals 0. It's a linear equation because we have powers of 1, okay? So that's linear. Quadratic then means that it has powers of 2, right? So you see things that are squared. So again, in algebra, that looks like things where we'd have like x squared plus 3x minus 1 equals 0 or equals y. It doesn't matter. The point is if I'm trying to solve this right here, I've got a power of 2 as my highest power. Now, there might be situations where we have higher powers as well, but they solve in the same way that the powers of 2 might solve. Okay, so there's not like an extension of that makes it more challenging. But we need to decide what kind of an equation we're dealing with because they do solve differently. So let me make a point about what that means. So if you remember solving an equation like, let's put up what I had before. I think that's what I wrote. If you were trying to solve this equation, 2x plus 3 equals 0, your goal would be to get x alone on one side and move everything else to the other side, right? Okay, so that's like the process by which we solve a linear equation. When we got to quadratics, which was probably in Algebra 1, like the latter part of Algebra 1 for you in high school, and you had things that looked like x squared plus 3x minus 1, you had multiple ways to solve them. And none of it involved leaving x on one side and everything else to the other side. It didn't do that. And in fact, because there's usually two x's involved, right? There's usually a squared term, like there is in my example, and then there's usually a term that's not squared. So how would I get just the x's there and not everything else over there? It becomes a more complicated situation. And so there's three different ways primarily that you learned to do this. Two of them that you probably would sort of gravitate toward, and one of them that you're like, I don't want to do that again, okay? So the first one that people usually learn is factoring. That's what I had you do on your gateway, factoring. We look and we see, do they have anything I can pull out of everything? Can I break it apart into two pieces, right? That's factoring. Okay, so that's one option. A second option, the one that sort of is our next go-to, is usually quadratic formula, right? It looks like this. It goes x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. I'm not asking you to remember it right now, but nod your head if that sounds familiar. Okay, so that was a second option. And you usually sort of like pushed into that option when it wasn't easy to factor or maybe wasn't possible to factor. Okay, so those are usually people's go-tos, those two. And the third option that people sort of shy away from is called completing the square. Nod your head if that phrase sounds familiar. Okay, so I don't think we have any completing the square examples, but I do want to mention it as a third option. Okay, it is something else that can be done. Completing the square is actually where the quadratic formula comes from, right? If you use the general form for a quadratic formula and you complete the square, it creates a quadratic equation. It creates the quadratic formula. So like that's where it comes from. But it's used for more than one thing. For what we're doing here, could it be used to solve it? Yeah, it could be used to solve it. It's also used for graphing purposes, right? How do we graph a parabola? How do I find out where the vertex is? Those kinds of things are used for completing the square, okay? So those are the three options. Number two, if only one trig function is present, we're going to solve the equation for the function, okay? So like if there's only tangent, great. We're going to be able to figure out what this is. We're kind of going to try to get tangent in some way, shape, or form by itself with everything else on the other side. Or we're going to try to factor things that have tangents in them and then go from there. But we're going to be in good shape. Okay, so if we have only one trig function, that's what we're going to do. But if we have more than one trig function, like maybe there's sines and cosines inside of the problem. Okay, well, I can't do that. It's almost like having x's and y's. It's not exactly the same, but if you have both of those pieces, it complicates things, right? So when that happens, we're going to rearrange it so that the equation equals 0, much like we would with a quadratic formula or a quadratic equation. Get everything on one side, 0 on the other side. And then we're going to try and do some factoring. And the factoring that we're going to try and do is to isolate like the sine and the cosine from one another. Right? We're going to try and separate them in some way. That's the third option. And then the fourth one is to try to change the way it looks with identities. So if you don't have it out yet, grab out the identities sheet that's 3-2, 3-3, 3-4 that's got those different pieces on there. That way it's sitting there if we need to reference it. Again, I don't know if we'll get to that today, but we might. And if we do, you've got it there sitting and you don't have to go searching for it, okay? Okay, are we ready? So you can see how some of this plays out. Okay, we're going to take things real slow. We've got 2 days to do this, right? So I'm not trying to rush through anything. So if you need me to pause and ask a question, like you should do that always. But I mean, really, truly, we got time. Pause and ask me a question so we make sure we can get this down, okay? All right. If you don't have the form paper with you, it's okay. Just, it'll be all right. We'll be okay together. I'll bring up what we need when we need it. All right, so here's a very a straightforward one first, where we're not actually solving. We're just going to decide if this is actually a solution. This occurred in an algebra course when you did it as well, where somebody said, is this ordered pair on the line? And you plugged in the x value for x, and you plugged in the y value for y, and you saw if the two sides were the same. So that's what's going on here. This says, use substitution to determine whether the given value is a solution for the equation. So what it's telling you you're going to do is you're going to take this value for x and you're going to put it inside of the equation. And you're going to see if the left-hand side and the right-hand side are equal. If they are, it's a solution. If they're not, it's not a solution. Nod your head if that makes sense. Okay? This is one of those techniques people try and tell you, like on an ACT or a standardized test. It's not the most efficient way of solving a problem, but if you've got an equation and you've got 4 answer choices and you're not sure what to do, you could take them one by one and plug them in and see if they work. Okay? That's the kind of thing you're seeing happen here. So this says tangent of x equals square root of 3. So we're going to put in tangent of pi over 3 equals square root of 3. Now this pushes back into the unit circle, right? Okay, we know pi over 3 on the unit circle. Since it's been a weekend, let me draw that in there. Our tangent of pi over 3 would be up here-ish, right? So we're somewhere like this as our angle. That pink is not a good color. Let's try something different. How about green? Okay. So this spot right here is my pi over 3 angle. And this has an ordered pair. Remind me, what ordered pair goes there? Right, 1/2 and square root of 3 over 2. Everybody nod your head. You've memorized that. You got that down, right? Fabulous. Also remind me, what is tangent in terms of those values? It's y over x. Fabulous. So we're going to change this value into the y, which is square root of 3 over 2, over the x, which is 1/2. Okay, all good? What do we do when we're trying to simplify a fraction over a fraction? We multiply by the reciprocal of the denominator, right? The reciprocal of 1/2 is 2 over 1. Notice I'm just working with my left-hand side over here. I know what the goal is to get it to be. I don't need to do anything on the right-hand side, right? It's just going to be what I'm trying to get to. And as I look at this, we see the 2 cancel out, and lo and behold, what value shows up on the left-hand side? Yep, square root of 3. And square root of 3, of course, does equal square root of 3, so this is a solution. Yes, it is. It works. Now, let's say that they had not given us pi over 3. They had given us, say, pi over 6. If we'd done pi over 6, the values here would have been flipped. I would have had 1/2 on top, square root of 3 on bottom. And as I got to the end of the problem, I wouldn't have gotten square root of 3 over there on the left-hand side. I would have had 1 over square root of 3. And if I rationalized it, I would have had square root of 3 over 3. Neither of which is the same as the right-hand side. And if that happens, then is it a solution? No. The answer is no, it doesn't work. It's not a solution. Okay, so that doesn't actually help us in terms of finding the solution, but if I'm given a potential solution, I should be able to decide, does it work or not? Does that make sense? And I should be able to verify it, right? Like my math lab is just going to say, does it work or does it not work? They're not going to be able to see your work to do this. But if you have a question like this on a quiz or on a test, you should be able to work it out just like I've done here on the left-hand side and verify it, right? So if I were to ask this question, it would say something like, is it a solution? Verify your answer. Or show me why, or explain, or something like that. And you'd be able to do a few steps to be able to show, yes, it does work, or no, it doesn't. Is everybody good so far? Okay, wonderful. Now let's take a look at what happens when we actually find solutions. Now, I will tell you, this word all is not going to be your friend. Finding all solutions is a harder thing to do than some of the other questions we're going to ask. So we're starting out with the all solutions, which makes it tricky, but we're also starting out with an equation that's kind of friendly. So why does this equation sort of look friendly? Well, if you take a look back at our different strategies here, it's in strategy number 2. There's only one trig function present. That makes it kind of friendly. Okay? So let's take a look at what we have. We have 2 sine x plus 3 equals 4. And strategy number 2 says what we're supposed to do, just like we would have any other, like equation where, like, let's just say this said x, right? If it said 2x plus 3 equals 4, you'd know what to do. What would you do? Run through some steps for me. What's the first thing you'd do? You'd subtract a 3. What's the next thing you do? You divide by 2, and you're going to do the exact same thing here. Okay? So we're going to start out with, I know it says what did I have? Tangent? Let me get the mess going away. Sine. I know it says sine, but the first 2 steps are going to be exactly the same as it is in algebra. We're going to subtract the 3. We're going to divide by 2. So let's do that. So we're going to subtract 3. So now I have 2 sine x equals 1, and I'm going to divide by 2. And I get sine of x equals 1/2. Okay, now if it didn't say sine x, it just said x, we'd be done, correct? But it does say sine of x. This value is on the unit circle, right? Again, that's another reason why this is a nice place for us to start with a question. This is a sine value. Sine values on the unit circle correspond to which ones? X, y, or a ratio between them? What is it? It's y. And I have y values in my unit circle that are 1/2, right? So let's sketch that out so that we can remind ourselves of where we're going to as we look through these. What angle measures give me sine values or y values that are 1/2? Pi over, oops, hang on, I think I drew it wrong. Pi over 6, that's the one I want to draw, right? Yep, pi over 6, okay. And what else? There's 2 within one rotation. There's always 2. 5 pi over 6, you got it, very good. So the next one is over here at 5 pi over 6. That's not drawn very well, but I think we can deal with it, right? No problem. Now, we all should also recognize that that's not all the solutions, right? Because unit circle, just if I'm looking at from 0 to 2 pi, that's 2 solutions, but we can keep going around and around and around, right? And I can keep going around and around and around, and I keep getting the same places. So while pi over 6 is a solution, so is 2 pi plus pi over 6. And so is 2 pi plus 5 pi over 6, right? I can go around again. I can keep going around the circle multiple times and get multiple different solutions. Okay, everybody good so far? So the question becomes, how do I write that? Okay, so to start with, we're going to write down what these solutions are. And we're going to write them on 2 different lines, like this. Okay, so if you only get to here and then you don't know what to do after this, you've still done the majority of the work, okay? So I don't want you to feel like my math lab's not going to count you right, but if you were doing a quiz or a test, I would count you partially right, right? You've done a lot of the work to get here, okay? The question is, what else do I need to do? Well, we just said we should be able to take that value and add 2 pi to it, right? And we should be able to add 2 pi to it again, and again, and again, forever. So how do I express that? Well, you've seen it before. We saw it back in chapter 2. You express it like this. You write down plus 2 pi. This would add 2 pi to it one time. And the way you add 2 pi to it multiple times is you write down next to it k. Now let me identify what k is. Well, k has to indicate that I can add 2 pi to it over and over and over. In other words, I can add 2 pi to it one time, so k can be 1. I could add 2 pi to it 2 times, so k could be 2. I could actually also subtract 2 pi from it, right? So k could be -1. And I could subtract 2 pi from it twice, and k could be -2. What kinds of numbers am I indicating when I give those values? What are those? Whole numbers, bigger than that though, that's part of it. Not real numbers, because that would give fractions and decimals, and I don't want those. Integers. Integers include the whole numbers that you mentioned, and their opposites, the negative. And they also include 0. If I put 0 in here, it just eliminates the piece at the end, right? I get 5 pi over 6, and I get pi over 6, which are answers as well. So the last thing that I need to do is I need to identify that k is an integer. And there is nothing special about k. It might be that my math lab tells you to use n or something like that. K is what I have in my notes, so I think that's what your resource is currently using. But I have used resources before where they say to use n. Okay? Doesn't matter. It's just a dummy variable, right? It could be any letter you want. I would not use x since x is already my problem, but probably anything else would be okay, all right? So this is our solution where it includes all possible values that work. Okay, how are we feeling? Okay so far? Okay. Now, if you take a look at this one, what's the difference in this question? I don't need all the solutions, right? It identifies to only do them on one rotation of the unit circle. If the last question had said that, I would have simply stopped when I found pi over 6 and 5 pi over 6, right? Okay, does that make sense? So this identification where it limits your values is a helpful thing. It eliminates that last step that we were looking at. Now, that should seem like that makes this problem a little bit easier, but do you know what makes this problem a little bit harder?
The 3 with the x.
What's that?
Is it the 3 with the x?
That's part of it, the 3 with the x. There's one more thing too. It's cotangent. Why is cotangent harder than sine? It's not specifically on the unit circle, right? I mean, it's there, but it's there as a ratio of things, right? I have an x and a y that have to be compared. Whereas on the unit circle, if I'm dealing with sine or cosine, it's just there and I see it. Okay, is everybody tracking? Okay, cool. So the first thing let's identify is that we need to figure out how we get the values where this square root of 3 happens. We'll deal with the 3x, just like you mentioned, but we're going to deal with that secondarily. Okay, I want to first deal with the cotangent issue. How do I find cotangent values that give me square root of 3 over 2? Or square root of 3, excuse me. So the first thing to do is to recognize maybe which quadrants we're in. Let's start there. Where in the world is cotangent going to be positive? Because it says positive square root 3. Which pieces of this graph? 1, it's always going to be 1, right? Where else?
3.
And 3. Yeah, so my answers are going to be in 1 and 3. Okay, is everybody good with that so far? Okay, so I've already eliminated sort of 50% of the things I could have written down for my angles. That's a good first step. The other thing is to recognize that it has a square root of 3 in it, right? And there are places on our unit circle that have square root of 3s, and there are places that don't. So let's just look at quadrant 1. In quadrant 1, where do you have square root of 3s show up? Like what angle measures? Pi over 6 and pi over 3. Okay, everybody good with that? So it's pi over 6 and pi over 3, and we first need to figure out which of those we're referring to. So let me put them in here, and let me put the ordered pairs so that we can remind ourselves what they look like. So we mentioned this one before, and this one, actually the second one, the pi over 3 is the one that we mentioned before. It was 1/2, and then, square root 3 over 2, right? And the pi over 6 is the reverse. It's square root of 3 over 2, and then 1/2. Is everybody good so far? Okay, so in order for me to get square root of 3, I need to make sure that I'm dividing these in the right order. So what is cotangent? Is it y over x or x over y? It's x over y. So this cotangent is going to be x over y. Not to be confused with the x, that's a 3x, but it's the unit circle values I'm thinking of here. Okay, so which of these, if I divide them, the pi over 6 value or the pi over 3 value, is going to be putting it in the right order? The pi over 6 value. And if you're not sure, you can check. If I take square root of 3 over 2, this is the pi over 6 value, and I divide it by 1/2, right? This is actually a lot like the last problem. I'd flip, or not the last problem, the first problem, I take it back. I would flip this and I would, like that, right? I'd multiply by the reciprocal of the denominator. These would eliminate and I'd have square root of 3. So it is the pi over 6 value. That's one of them. So I'm going to write the angle. Our angle is 3x. So hold tight with me. It's 3x. It's going to equal possibly pi over 6. It's not the only thing it could equal. There's a reason I'm leaving the space there, so leave yourself some space and you'll see why. We need to find the corresponding value in quadrant 3 that works with this. So what value in quadrant 3 down here is going to have the same reference angle, remember we talked about those, as pi over 6? 7 pi over 6. Fantastic. You guys have come so far. You probably don't even recognize it, but you should. This is 7 pi over 6. Okay, so we work to get the first one, and the second one usually comes at it a lot easier because we've already done the work. We already know. It's going to be the corresponding pi over 6 value. It's got to be. Okay, pretty good so far. Okay, we're supposed to be finding all of the values on the unit circle from 0 to 2 pi, right? Not including the 2 pi, but we're supposed to find all of them. Now, if I do just this and I divide by 3, I will find 2 values. Both those values will be correct, and I will have done a good portion of the problem. I'm still missing some stuff, but I've done a lot of it. Okay, everybody good so far? So if what you can do right now is simply divide by 3 and then you forget the next step, you've still found a good portion of the problem. Okay? The problem is that you're actually going to miss some of the solutions, and here's why. Think about what happens when you go around the circle twice. Okay, if I went around the circle twice, I'd go 4 pi around, correct? But if this said 2x at the beginning equals something between 0 and 4 pi, and I divide by 2, my value will be between 0 and 2 pi. Are you with me? If I start and I go from 0 to 4 pi and I divide that by 2, I will be between 0 and 2 pi. But my angle doesn't say I'm going to divide by 2. It says I'm going to divide by what? 3. So if I went around 3 times for the unit circle, right, all the way around 3 times, I'd get 6 pi, right? Okay, 6 pi. And if I divide 6 pi by 3, what do I get? 2 pi. So what does that mean? Well, it means that going for unit 1, or for quadrant 1, where I have quadrant 1 over here, pi over 6, and quadrant 3, where I have 7 pi over 6, I have to go around 2 pi more, 2 times. I'm going to have 3 times as many solutions. So normally, if this just said x equals, I'd have 2 solutions, because the unit circle, in most cases, gives me 2 answers, right? Most cases. But because this says 3x equals, I'm going to get how many solutions? 6. I'm going to get 3 times as many solutions because it says 3x equals. So what does it look like? Well, it looks like I've got pi over 6. That's cool. And then I'm going to have, let me see how I want to write this. Let me do this. Let me give myself some more space. I'm going to skip just a little bit of space underneath this and write the next one. I'm going to have the pi over 6, and then I'm going to add 2 pi to it. That's going to go around the circle one more time. And I'm going to write that value next to it because it's equal. What is pi over 6 plus 2 pi? Grab a calculator if you need to. I don't care. What is that going to give you? What is it? 13 pi over 6. You got it. But I have to do that twice. So I also, again, I've left a little bit of space on purpose. I have that 13 pi over 6, and I'm going to add another 2 pi to it because I have to go around 3 times because it says 3x. So in some sense, if you want to make yourself a note, this tells you that I need to add, so I have 3 rotations, right? I'm going to add twice, so I've gone around 3 times. What is 13 pi over 6 plus 2 pi? 25 pi over 6. Okay, is everybody good so far? I need to do the same thing with the 7 pi over 6. And to try and organize myself a little bit, I'm going to draw some lines in between these because I'm going to have to come back and finish them out in just a second. I'm just trying to establish the adding of the 2 pi every time, okay? So I've got the 7 pi over 6. I'm going to give you some space over here too. And then I'm going to add, same thing, 2 pi to this one. So what is 7 pi over 6 plus 2 pi? 19 pi over 6, very good. And I'll put the other one over here. I have 19 pi over 6 plus 2 pi. What am I at on that one? Am I at 31? Does that sound right? 31 pi over 6. Okay, but the goal was not to find what does 3x equal. The goal is to find what x equals. So what am I going to have to do in all of these scenarios? Divide by 3. And you can write divide by 3 if you'd like. You could also write it how? How could we write it instead of divide by 3? Because there's fractions involved here. Multiply by 1 over 3. Okay, so feel free to divide by 3 if you wish. I'm going to write mine as multiplying by 1 over 3. Because it's sort of friendlier to look at fractions, multiplied by fractions, than divide it. Okay, so let's just start with the very first one. If I take pi over 6 and I multiply it by 1/3, what do I get? Pi over 18. Okay, so this is one of my solutions right here. Let's try one more. So if I take the 3 pi, or 3x equals 13 pi over 6, and I multiply by 1 over 3, what am I going to get for x? 13 pi over 18. Do you notice a pattern of what's happening as I'm multiplying by 1 over 3 every time?
Just adding 12.
To the denominator, right? I'm actually multiplying the denominator by 3, right? My denominators are all 6s right now. And when I multiply by 1/3, they're all going to become 18s, correct? So if you want to see the multiplying by 1/3 on every step, feel free to do so. But if you recognize the pattern at this point, you could actually recognize that each one of these is going to be what they already are, but over 18. I'll only write it to the side. I'm running out of space. 7 pi over 18 right there. Down here, I will have 19 pi over 18. And then over here, I will have 31 pi over 18. Okay, so let's say, for instance, that you forgot how many times you're supposed to add 2 pi to this, and you're like, I don't know, maybe I've got too many answers. I don't remember what that rule of thumb was supposed to be. It's just I'm in the moment. I don't know what to do. How could I check to make sure that these 6 answers are all between 0 and 2 pi, that I haven't sort of gone over 2 pi? What could I do? Any thoughts?
36 pi over 18 is 2 pi.
Okay, so one way to think about it is what does 2 pi look like when it's over 18? It'd be 36 pi over 18. Very good idea. Any other thoughts? Well, along those same lines that George mentioned, what we could do is we could take the biggest one we have. I'm just going to start with the biggest. You could take any of them, but take the biggest one you have. Take your calculator. What is 31 over 18 in decimals? You can give it to me in decimals if you wish. That would actually be preferable at the moment. What's 31 over 18?
1.722.
1.722. And is 1.722 smaller than 2? Yes, it is. So at the very least, what I know is that the answers that I have are between 0 and 2 pi. Because 31 over 18 was the biggest, and we established that it's about 1.72, and it's smaller than 2. Okay? How do I know how many answers I'm supposed to have? What's the rule of thumb again? Well, this says 3x. I should have 3 times as many answers as I normally have. Most of the time, I have 2 answers on the unit circle, so I should have 6, and I do have 6 of them. And if you really wanted to check to make sure that each one of these is really a solution, what did we do in the first problem? We plugged it in. Could we plug in each one of these 6 solutions and actually see if the cotangent works for that? We absolutely could. Now, the way we'd have to do it in the calculator is to plug it into tangent, right? And then reciprocate, right? Do the reciprocal of it, flip it upside down. Okay, is everybody good so far? There are how many solutions here? 6. I would actually contend that on this particular one, it might have been easier to do that than to find 6 solutions, right? Sometimes it is. All right, let's take a look at another one. Why does this one, or how, let's go with how does this one look different than the previous ones we've done? It's equal to 0 to start with. We don't have to do any of that, but didn't the last one have that? Nope, it didn't. Sorry, it's equal to 0. That's definitely one of the ways. Not the one I was thinking of, but you're right. It's got a half angle in it. That's another way. We've got cosine, so we're back in the cosine world. That's nice. And when I have values like 0, like Jaden mentioned, 0s and 1s do not usually give me 2 answers on the unit circle, right? Sometimes they do and sometimes they don't. Depends on what the number is. 0 will, but if this said 1, it wouldn't. So those whole number pieces we have to be a little bit more cautious with and ask ourselves, where does this work? So let's actually start with that. Where on the unit circle, this is where we're going to start every time, where on the unit circle is cosine going to be equal to 0? Where does that happen? What's that?
Somewhere on the axis.
It's going to be on an axis, exactly. You've got 0s, 1s, and negative 1s. It's going to be on an axis. Which axes is cosine going to be 0 on? Y-axis, very good. And it will be 0 at the top and at the bottom, right? Everybody good so far? So this one, there's going to be two solutions at least. If this said cosine of angle theta equals 0, I would have two answers. And the two answers would be what? What is this angle? Pi over 2. And what if I go all the way to here? 3 pi over 2. Okay, everybody good so far? Okay, so coming over here, just like when we had 3x, we have theta over 2. We're going to write theta over 2 equals pi over 2, and then we're going to write theta over 2 equals 3 pi over 2. Okay, everybody good so far? How do I solve then for theta? Because that's the question I'm being asked, not what does theta over 2 equal. What does theta equal? What would I have to do to solve for that? Multiply both sides by 2. Okay, so let's do that to both equations. The first one, what will theta equal? Pi over 2 times 2. Pi, thank you so much. I promise I can wait longer than you guys can. All right, good deal. How about 3 pi over 2 times 2? 3 pi, right? Now, if I put both of these answers into my math lab, it's going to tell me I'm wrong. Why? What's that?
Do you have to do it 6 times?
Nope, we don't have to do it 6 times. How do I know how many solutions I should have? The last one, it was 6 times. Why did I know that there were 6 solutions? Because it said 3x. Okay, so I don't have 6 solutions. But if I put these answers both in, it's going to tell me I'm wrong.
Should we have one?
Should we have more? No, we shouldn't have more.
Okay, so we have one.
Cecilia?
Since it's like division instead of multiplying, would we have like less than usual?
Yes, we could. This is theta divided by 2. The last one was 3 times. I had 3 times as many solutions. So if I have theta divided by 2, how many solutions do you think I'm going to have? Half as many. Why is 3 pi not a solution in this problem? Because it's larger than 2 pi. I'm supposed to be giving answers between 0 and 2 pi, and this one isn't. It's a solution. It works. If you put 3 pi into your calculator, it is absolutely 100% going to work. But it doesn't satisfy the directions of the problem. The problem wanted only the solutions between 0 and 2 pi. So this one does not actually satisfy the directions of the problem. This is one of those moments where it's like read the directions really carefully kind of things. If you guys ever done that problem thing, it's like a paper that somebody gives you and it's got like 20 steps. And the first step says read all the way through this before you do anything. But if you just start it and you don't read all the way through it, you're doing all these crazy things. And the first thing was, it said, don't do anything else on this paper or something like that. Or, like not the first thing, but later on it says don't do anything on the paper, right? You've done all these steps. Read those directions. They're important, okay? And if you forget and you get to the point where you put both of these solutions in, maybe stop and say, did I read the directions? What did I miss? Because I'm pretty sure I did it right. Oh, that's right. This number is too big. Okay. Good? Okay, let's try another one. What makes this one look harder? The angle's got addition in there, right? We haven't had that yet. We had addition, multiplication, we had division. We've not had addition and subtraction. It's really not a big difference, but it still looks different. Okay? Everybody good so far? So if we just simply ignore what's here for the moment, and it just says tangent of something equals 1, we're back to doing exactly the same thing that we've done before. We need to look at the unit circle. We're going to do that every single time. We're going to look at the unit circle and figure out where on the unit circle is this going to happen. Okay? So that's where we are first. Where on the unit circle do I have tangent values that are equal to 1? Okay, again, tangents and cotangents are harder to do, but if I want tangent to equal 1, what has to happen with x and y? They have to be the same, right? Tangent's a ratio. The only way I get a ratio to equal 1 is if the numerator and the denominator are the same. And in the terms of tangent and cotangent, that would mean the x and the y's would have to be the same, right? Okay, very good. Y'all are doing great. So where on the unit circle are the x's and the y's exactly the same? Whoops. Pi over 4. Oops, I wrote that wrong still. 4. And then what was the other one? 5 pi over 4. Okay, everybody good so far? All right, and it did say 0 to 2 pi, so we've got that in our midst as well. We don't have to do the k plus, or the 2 pi k like we did in the other one. Okay, so this is going to say whatever my angle measure is, which is pi over 2 plus, theta over 2 plus pi over 3, and it's going to equal each of these values, pi over 4, and then I'm going to do another line, just like I've been doing, 5 pi over 4. Okay, all good so far? At this point, aside from the fact that it looks like theta, right, this is algebra 1. You have a variable, you have a linear equation, I'm trying to solve for theta. So looking at the first one, theta over 2 plus pi over 3 equals pi over 4, weird numbers aside, what's the first thing I need to do? Subtract the pi over 3. So I've got theta over 2 left on the left. Again, grab a calculator if you want to, I don't care. What is pi over 4 minus pi over 3? Ooh, it's negative. Okay, negative pi over 12. We're going to have to deal with that in a minute. Why? Because it's less than 0. So we're going to have to do something. We should have 2 answers potentially when we're done. We might. We need to make sure that if we change something up just a little bit, it doesn't mess something up. So we're going to have to look into that. But for right now, we're good. And then what would I do next in order to solve that? Let me shift this one down a little. I'd multiply by 2. You got it. Okay, so if I do this and I multiply by 2, this is theta equals negative pi over 6. Okay, everybody good? Negative pi over 6. Okay, let's do the same thing to solve the second one right here. We'll come back to that. We're not done, but let's just solve the other piece. Okay, same steps, right? I'm going to subtract pi over 3. That's going to give me theta over 2 equals. So what is 5 pi over 4 minus pi over 3? 11 pi over 12. Okay, pretty good? Cool. What's my next step? Multiply by 2. So if I take 11 pi over 12 and I multiply by 2, what am I going to get? 11 pi over 6. Now, 11 pi over 6, is that on the interval I'm looking at? Yeah, 11 pi over 6 is definitely on the interval from 0 to 2 pi, so that's not a problem. We do need to be careful that we didn't accidentally miss something when we did the first one. So let's check and see what happens. When we originally said that the original value was pi over 4, that's what created that negative at the beginning, correct? It was when we found pi over 4. Let's find another expression for the pi over 4 just to make sure we don't have another solution that we accidentally missed because we did this subtraction thing. Okay? So if I were to have gone around the unit circle all the way and then back to pi over 4, right? All the way up, all the way around, I did that the other way. All the way around and then back up to pi over 4, how far would that be? In other words, if I were to take this pi over 4 and add 2 pi to it, right, that'd be going around one more time, what would I get? 9 pi over 4. Okay, is everybody all right with that? That would be another potential solution, right? We might have another solution here. We want to be sure. So we're going to take that same value that we had, theta over 2 plus pi over 3 equals, and we're going to do 9 pi over 4. And why are we doing 9 pi over 4? Because when we subtracted the pi over 3, it ended up negative. So there might be another answer here, and we want to be careful that the subtraction didn't just sort of accidentally lose something. We don't want that to happen. So we're going to run through the same steps. We're going to subtract the pi over 3. And you guys are going to check and find out for me what is 9 pi over 4 minus pi over 3. I don't have this one written down for some reason, so somebody's going to have to help me out. What's 9 over 4 minus 1 over 3 in fraction? I think it's going to be something over 12. Do you have it, Jaden? 9 over 4 minus 1 over 3. That's the one we had before, so I don't think so.
23 pi over 12?
That sounds right. Okay, is that all right to everybody? All right, and then what's our next step? Times 2. And if I simplify that, I've got theta equals, and now I have what? 23 pi over 6. That's definitely bigger than the pi over 6. But the question is it within a unit circle? And the answer is no. If I take 23 over 6, what decimal does it give me?
12.04.
It gives me 12. I think that's too big. I think so. I think you put the pi in. Just the 23 over 6 is what I was talking about.
3.83.
3.83. Okay, it's almost 4 actually, right? 3.83. That's bigger than 2. So this one did not end up giving me any additional solutions. Could it have? Yes, it could have. Do you still need to check? Yes. If you forget and you happen to get lucky, are you lucky? Yes, right? You might not check something and it might work out in your favor. It happens all the time. But this is also a potential place where it could have gotten a solution. So how many solutions were there on this one? 1. And does it make sense from the fact that this was theta over 2?
Yes.
Yes. That makes sense. Theta over 2, I'm probably going to get half as many solutions most of the time. Okay, so we will pick up with question number 6. That's actually a really good place for us to pick up next time because everything we've done today was linear. We're going to change next time and we're going to see what happens when things turn to quadratics. All right?
Why is